Okay. Okay. Can you see my slides?
Yes.
Okay.
Yes, ma'am.
This is a presentation I put together a few months ago when I was giving a 3-day reservoir engineering workshop. This is the third part of the presentation where I'll talk about simulation. This is a general outline of the presentation where I'll talk about a generalized model, some formulations of the model, advances in model formulations, stable time step and switching criteria, what is the linear solver, Cartesian grids and the reservoir definition, upscaling of grid properties, streamline simulation, geomechanics simulation, and then how do you treat PVT. I wanted to start with this just a general talk on what exactly is reservoir simulation. Let's see if this works.
I'm not very hopeful about that. My name is Yogashri. I'm the team lead for the business.
Hello, ma'am. Sorry to interrupt you, but I'm unable to hear this voice.
Oh, okay.
Audio is not audible.
Okay. Thank you for telling me that. Let me go ahead and when I say present.
And ma'am, I wanted to ask one more thing. We are going to record this session. So, is there any problem with recording of the session?
There's no problem in recording the session. I'm just trying to
Okay.
figure out how to share the sound. Let's see. It says turn the entire screen. If you're not able to hear it, I'll just go ahead and start with just the rest of the presentation. But that was just but the main idea of the presentation, that YouTube video was to just give you an idea of, what exactly is reservoir simulation and then the applications to industry. So now I'm going to start presenting my screen.
Yes, it is visible now, ma'am.
Yeah, it is visible. Good. So let me go ahead and get started with the generalized model. So any reservoir simulator consists of n plus m equations for each of the n active grid blocks. That makes the reservoir. So if there's n plus m equations, there has to be n plus m variables. So this represents the conservation of mass of each of the n components in each grid block over a time step of delta t, from t to the n to t to n plus 1. Because m constraint equations for a block involve unknowns only in a given block, they can be used to eliminate the m secondary variables from the blocks and the primary or conservation equations needed to be in discussions of model formation and the linear solver. So this is a primary conservation equation for a block I, which is here. So this is your m, n plus 1 at a given, at a given block, and times your time to the n, to all the n grid blocks, your flow rate, and then it's always equal up to your just different time steps. So m is the mass component of the I grid block, and qi is the interblock flow rate component from the I neighbor grid block to j to block I, and qi with the capital I is a well term. So this can be turned into a vector equation where f of I is the ith element of the vector f, and that 0 equals the entire model. The ith element of the vector f is the f of I. F is a function of the n vector unknowns, and p of I is the ith scalar element of p of I, which is p of I to the I grid block. So when you're applying Newton-Raphson, that gives this governing equation, where del P is PL plus 1 minus PL, and then the n times n matrix, A represents the Jacobian of del F over del P. And that's solved by the linear solver. So there is going to be another video on what's the Newton-Raphson method, but if you can't hear my audio, then I'm not going to go ahead and talk about the Newton-Raphson method here. And then this was going to talk about the Jacobian method too. But if you can't hear my audio, I'll skip this one as well. So for the generalized model, each Newton method requires a linearization of the constraint equations and conservation, linear algebra to generate the A matrix and coefficients, iterative solution of f of L, del F equals f of L plus A del P equals 0. Do some new PL plus 1 to obtain from the conservation equation the moles of each component in the grid block. In a flash to give the phase compositions, densities, and saturations, which allow the generation of the A matrix coefficient for the next Newton iteration. For model formulations, this is the interblock flow term, which is this governing equation here. So this uses phase mobilities, densities, and mole fractions evaluated at the upstream blocks. Implicit, so if you're using an implicit method, you're solving for the n time step by using n plus 1. For the explicit time step, you're solving n plus 1 by using n. So implicit, you're expressing the interblock flow terms using the new time level values of all variables in all grid blocks, using an operation order of n squared or n cubed. Impes is implicit pressure and explicit saturation. You take all variables in the interblock flow terms, explicit except for pressure, and eliminate all non-pressure variables from the linearized expressions from n plus 1. So the mass component. And then you have a sequential method where you use impes, but for a three-phase case. It requires solution for the impes pressure, followed by a solution of two saturations from a similar equation, where A elements are 2 by 2 matrices. And then this is a more common one, adaptive implicit. It uses different levels of implicitness in different blocks. In each grid block, each of the n variables may be chosen, explicit or implicit, independent of the choices in other grid blocks. Choices may change from one time step to the next. Aij is the regular size matrix. CPU expense per Newton iteration of the AIM model lies between those of the implicit and implicit models, tending toward the former as more blocks are taken implicit in pressure only. So when you're choosing a formulation, when you're solving for numerical simulation, implicit formulation is generally faster than impes for single well coning studies and for thermal and naturally fractured reservoir problems. Impes is generally faster for moderate or large number of variables, so greater than 4. Numerical dispersion is larger for implicit than for impes. What exactly is numerical dispersion? It's a difficulty with computer simulations of a continua such as fluids, wherein the simulated medium exhibits a higher dispersivity than the true medium. So here's some sample of, here's just some sample of what outcomes you can get from the IMPES versus the implicit oil rate and cumulative production. You get some similar results in the chart on the left. And then on the chart on the right, you could get some IMPES versus implicit GOR and water cut. These all come from SP monograph 9. So you'll notice that IMPES is in the solid black line and implicit is in the dashed line. And you get some similar results where the IMPES looks like it's overestimating the GOR compared to the implicit. And in this case, IMPES is underestimating your cum oil or your rate compared to implicit. So there's been some advances in model formulations where with relaxed volume, it relates to time step calculations. The use of the PL+1 to obtain from the conservation equation the moles of each component in the grid block. There's a flash to give phase compositions, densities, and saturations, which allow the generation of the A matrix. The volume balance error occurs because of the nonlinearity of conservation. Saturations do not add up to 1 that way, but mass is chosen to be conserved, and there is a volume balance error. A volume balance error is carried forward to the next time step by treating L+1 as del J, and then our summation of J, del Sj, equals 1 to the summation of J, Sj to the ith grid block, which conserves both mass and volume. So S is saturation. And Newton iterations and CPU time are reduced. So relaxed volume helps with the CPU time. There's also variable choice. In linear algebra, it's required to reduce the grid block's end conservation equation to the IMPES pressure equation, and that's influenced by the choice of variables. The influence is absent for black oil, moderate for moderate N, and up to a factor of 3 for a large N. And the choices of P and mole fractions or mole numbers are better than the choice of P saturations and phase mole fractions for a large N. And then the effective CPU time is small because the affected work on a small part of CPU is on a small part of CPU time. An IMPES reduction is absent in the implicit formation, and the last of the mentioned variable choices is preferable. Let me check on how to share sound on Google Meet. Okay. And then there's adaptive flash calculations. The work of EOS flash calculations can affect model efficiency when the linear solver does not dominate CPU time. There may be little need to perform most of that work in a grid block when P and composition are changing slowly. The use of internal intelligent criteria dictating when that work is needed can significantly reduce the total run and flash calculation CPU time. So there now talk about some stable time step and switching criteria. The observation that lower turnaround time can increase benefits from a reservoir study allotted a budgeted time period. IMPES is a conditionally stable formulation where the conditional stability stems from explicit treatment of non-pressure variables in the interblock flow terms. So this is what your T is equal to as far as your time step. So time step is dependent on flow rates, phase mobility, and capillary pressure derivatives. IMPES model will run stably, but may suffer from a weak link principle. On the AIM formulation, stable step depends on the number and identities of variables chosen in an explicit block I. Theoretically, delta Ti equals infinity if all block I variables are chosen implicit. For a large grid block problem, the AIM model would require CPU time or step no greater than the IMPES model, but would require significantly less time steps for a smaller total number of time steps. The most reliable and efficient AIM models in the future will stem from continuing research leading to the following. Delta T and delta T estimates which are accurate, implicit versus explicit variable choices, block by block, which are near optimal, and minimize total CPU time. So that's CPU time per step times the number of steps. Now I'll talk about the linear solver. The preconditioned orthomin is the most widely used method for the iterative solution for this governing equation that I showed before. There's nested factorization and incomplete LU factorization are the two most widely preconditioners. LU factorization is factoring the matrix A into the product of the lower triangular matrix and upper triangular matrix U. Nested factorization performs exceptionally well when transmissibility is associated with a particular direction in the structured grid, dominate those in other directions uniformly throughout the grid. The literature search have failed to establish whether nested factorization or LU factorization are better. And then when nested factorization works well, it is faster than the LU methods. So what exactly is nested factorization? So this comes directly from an SP paper 12264. It constructs the block lower and upper factors using a procedure which adds one dimension at a time to the preconditioning matrix. Factorization procedure, preconditioning matrix. The factorization procedure conserves material exactly for each phase at each linear iteration and accommodates non-neighbor connections arising from treatment faults, completing the circle and 3D coning studies, numerical aquifers, and dual porosity permeability systems. So I'll talk about the Cartesian grids and reservoir definition. Non-Cartesian grids can reduce grid orientation effects and provide definition and accuracy near wells, fault, and highly heterogeneous areas, and so on more efficiently than Cartesian grids. Most examples used, however, to study those effects are highly adverse to mobility ratio displacements in homogeneous horizontal reservoirs. And Cartesian grids can provide adequate accuracy, reservoir, and near well definition efficiently in some cases, even without local grid refinement. Now I'll talk a little bit about gridding. The aim of gridding in reservoir simulation is to turn the geological model from the fields to a discrete system on which the fluid flow equations can be solved. In classical finite difference scheme, the point values of pressures and saturations are used as solution variables, and differential operators that appear in the fluid flow equations may be expanded as difference expressions of these point values to some order. So there's two issues. The accuracy at which geological description of the reservoir is matched, and then you have the discretization of the flow equations. So this gives a YouTube video of gridding. Let me go ahead and share my screen again to see if I can share audio. Okay.
Now,
So I'll go ahead and share this tab.
Hello my friends. In this video I am going to teach you how you can build a simple model in Eclipse, and we are going to talk about the grid section in the data file. If you remember from the run spec section, we are going to build a reservoir which has a 10 grids in the x direction, 10 grids in the y direction, and 3 grids in the z direction. We already assigned the number of grids in the run spec section, but we didn't identify what will be the properties of each grid. So in the grid section, we are going to say what will be the dimension of each grid itself, and what would be the porosity and permeability of each cell in our model. So we need couple keywords to assign the properties. First keyword is a tops keyword. What is a tops keyword? Tops keyword is going to identify the depth of your reservoir. So imagine this is a ground surface, and you have an underground reservoir like this. Tops keyword is identifying the depth of the reservoir from the ground to the top of your top surface of your reservoir. So in our reservoir, we have 10 grids in the x direction, 10 grids in the y direction. So in total, we have 100 grids in the surface of our reservoir. So we need to identify what is the depth of these 100 grids at the top surface of our reservoir. So we need to write tops keyword in the grid section of our data file, and we have number of the cells in the top layer, which we have 100 cells in our top surface of our reservoir, and the second value 4000 is showing the depth of the reservoir. So this depth in our data file is 4000. And if you remember from the run spec section, we told the data file that we are going to use the field units, so it means that this 4000 is 4000 feet. So we have the top surface of our reservoir has 100 grids, and the depth of our reservoir is 4000. And then we are going to say what will be the dimension of our grid, dimension of each grid in the x, y, and z direction. So to identify the dimension of grids, we need to use dx, dy, and dz keywords. So these dx, dy, and dz are showing the size of each block, each grid block. So size of each of these blocks. So what you need to do is that write dx.
Hello, ma'am. Sorry to interrupt you.
How many grids
Yes.
in total you have?
Ma'am, please turn off your mic because sound is repeating in that one.
Oh, okay. Well,
Yeah.
the thing is, I wanted to, you can't hear this video?
Yeah, I am able to hear this video, but the sound of the video is repeating through your mic also.
Oh, yeah, I
Yes,
can't.
ma'am.
Oh, okay, let me turn off my mic too.
Yes, ma'am.
We have 10 grids in the x direction, 10 grids in the y direction, and 3 grids in the z direction. So in total, we have 10 times 3, so it will be 300 grids in total. And dx is showing what is the x delta x of each grid. So you have total 300 grids, and we are saying that the dimension of x in our delta x in our grids is a 5 feet. So 5 feet is a dimension of each grid in the x direction. So similar to that, we need to identify what is the dimension of each grid in the y direction, which, for example, in this example, we say that we have 300 grids, and its dimension is 5 feet in the y direction. Similar, for the Z direction, we have 300 grids, and its size in the Z direction is 3 feet. So we have a grid which has 5, 5, 3 dimensions. Don't forget to have a slash in the end of each dx, dy, and dz. Next step is so till now we identified the dimension of or size of our grid blocks. Right now we are going to assign permeability and porosity for each of these grids. For permeability, we are using perm x to identify the permeability in the x direction, perm y for
So the rest of the video ends up talking about how you can set up your other properties, but I'm going to go ahead and share my screen again. So back to this. So then now I'm going to talk about the upscaling of grid properties. Upscaling is substituting a heterogeneous property region consisting of fine grid cells with equivalent homogeneous region made up of single coarse grid cell with an effective property value. So this is performed of each of the cells' coarse grid and each of the properties needed for the flow simulation model. Essentially, this is an averaging procedure in which the static and dynamic characteristics of a fine scale model are to be approximated by that of a coarse scale model. So this is just a chart of how you can upscale, or a quick example of how you can upscale your grid properties. You're taking a sampling of this fine scale grid. You're going to coarsen the properties of that grid, and that's how you end up upscaling to having more grid blocks, having a fewer grid blocks, but the same size of the entire grid. So now I'll talk a little bit about streamline simulation. It differentiates itself from cell-based simulation, such as finite differences and finite elements in the phase saturations and components that are transported along flow-based grid, defined by streamlines rather than moved from cell to cell. It allows streamlines to be extremely efficient in solving large heterogeneous models if key assumptions in the formulation are met by physical system being simulated. Large relates to the number of active grid cells. Represents a snapshot of the instantaneous flow field and thereby produce data such as drainage, irrigation regions associated with producing injection wells, and flow rate allocation between injector-producer pairs that are not easily determined by other simulation techniques. And the key assumption is that the system is close to incompressibility. So here's another video of streamlined simulation. And I'll show, yeah, I have a lot of videos in this presentation, but I'll skip that video for now. So this is geomechanics simulation. So changes in porosity and permeability are more pronounced when rock failure occurs, such as compacting reservoirs or in high pressure injection operations. And these processes require more complex coupled geomechanical modeling. So there's two types of coupling. There's a pore volume coupling, where porosity in the reservoir model is traditionally treated as a function of pressure via rock compressibility. Pore volume changes are a result of complex interaction of fluid pressure stresses acting on the element of rock and temperature. The deformation of rock solid caused by the combination of stress and pressure changes results in changes in the bulk volume of an element. And then you have flow properties. You have dominant and more complex and fractured reservoirs where stress-dependent fracture aperture and reopening, creating fractures under injection can cause large anisotropic changes. The perm change are a function of some measure of effective stress, but are often simplified as a function of pressure. And the creation of new fractures can cause transition from initially single porosity media to dual porosity, and in such a case will also have an effect on relative permeabilities. So then you have a modeling of compaction and dilation. Compaction is generally treated as a 1D problem by assuming that there's only vertical deformations that take place, and each vertical column of blocks deforms independently. Porosity changes are calculated by modifying the conventional compressibility as a function of pressure only in the form of compaction tables. Dilation or increase in porosity is an important geomechanical mechanism occurring during stream injection in unconsolidated sands, and this has been modeled by compaction dilation tables. The major drawback is that dependence on stress must be ignored, or the change in stress must be estimated in terms of change in pressure. And they have much larger computing requirements because the larger number of unknowns per grid block and the stress solution grid must be larger laterally than the reservoir grid to eliminate the effect of boundary conditions, as wells extend up to the surface to provide subsidence solution. And now let's talk about Pvt treatment. So this describes the phase behavior of gas, oil, and water at reservoir and surface conditions. Water phase and water component are treated simply. Some partitioning is done to water with compositional models. There are two ways to calculate phase behavior in a reservoir model. There's black oil, which is the interpolation of Pvt properties as a function of pressure. And then there's compositional, which is based on thermodynamically consistent models, such as a cubic equation of state. There are some important facets of the Pvt treatment, such as number of phases and phase type, your two-phase flash, your density, component partitioning, gas-oil interfacial tension, black oil Pvt models, equation of state models, three-phase Pvt behavior, surface phase behavior, thermal model Pvt requirements, and then fluid initialization. This is the end of the presentation. There have been quite a few videos that I want to share with you all, but if you want to, this is just the gist of the reservoir simulation basics. You can connect with me on LinkedIn if you have any questions. Connect with me on Instagram, and then I also am on Twitter if you want to follow me there. So I'll go ahead and stop sharing my screen, and I'm open to questions.
So student, if anyone have any query or question, they can directly ask in chat box, or they can unmute their mic also.
Okay, Vishnu raised his hand.
Yes, ma'am. Good afternoon, ma'am.
What's your question?
My question is on chat box.
Oh, you have numerical instability in reservoir simulation, but what
I
about
have
it? What about numerical instability in reservoir simulation?
I run the reservoir simulation in Eclipse, and in 2014 production starts and in carbonate reservoir. So there is a difference between models using we are in reservoir simulation and we are predicting. So there is a numerical stability. So how we overcome this numerical stability in reservoir simulation?
You overcome numerical instability in reservoir simulation by using a different type of calculation. So you use your IMPES method, or you could use your implicit method. That tends to get rid of the numerical instability. And then you also have to reduce the the tolerance at which some instability is allowed. You have to reduce that tolerance, or you can increase the tolerance to keep. I'm sorry, you have to increase the tolerance. That way you can keep continuing your time steps. Any other questions?
Hello, good evening, ma'am.
Hi, Lalit.
Yeah. Ma'am, can you explain what is the main aim of well simulation in easy language, and which model we use mostly in our industry?
What do you mean, which model?
Like there are many types of models in these well simulation. So which is more easy to use and efficient?
I mean, it's a very broad question. It depends on what reservoir you're working in. So I tend to work in unconventional reservoirs, so shale reservoirs. So the model we end up using is, I mean, it's a pretty simple black oil model, but it's a horizontal model. And then, I mean, you can model a full wellbore too. And if you're working in a carbonate reservoir, you can, I mean, it really just depends on what your reservoir type is.
Okay, ma'am. Means it depends on the properties of a reservoir,
Yes.
individual reservoir.
Yes.
Okay, ma'am. Thank you.
Hello, ma'am. Our principal, sir, Dr. S.K. Vishnu is also here with us. So I welcome our principal, sir.
Thank you, sir. Thank you, ma'am, because you are far away from us. After that, you spare time for the country. So we are very grateful to you, ma'am, because you enlighten us, motivate our students, and give the overview or the basic concepts of this reservoir engineering. So we, on behalf of entire engineering college Badmer faculty, staff and student, I welcome you, ma'am, and we are very much thankful to you for sparing time for us.
Thank you for having me. I enjoyed presenting.
Thank you, ma'am. But you spare some time for your country, then it's very, we can say it's really remarkable because you are very far away from us. After that, you accept our invitation and spare your time and enlighten us by your knowledge and experience in the reservoir engineering fields. So we are very much thankful to you, ma'am. And in future, you spare some time and motivate our students because we have the petroleum branch in our institutes, and the another is chemical engineering. Except these two, we have seven branch. One is civil and electrical, mechanical, all fundamental branch we have. So
Okay.
it's
Of course. Well, thank you. Again, thank you for having me, and thanks for the kind words.
thank you, ma'am. Thank you.
Does anyone have any other questions?
Hello, ma'am.
Yeah.
Hello, ma'am.
Yes.
Yeah, ma'am. Being a petroleum engineering student, how can we make our career in reservoir simulation in initial phase?
Well, I would suggest you focus your research in reservoir simulation and then make sure your placements are the opportunities that you look for and the placements that you get are focused in reservoir simulation. You have to set yourself up where your research was in reservoir simulation, whether if that was your master's or whether if that was an undergrad. So I would say just take classes that are in reservoir simulation, focus your research on reservoir simulations, and you have to market yourself where this is what I want to do.
Yes, ma'am, but in India, it is very difficult to find out the training in reservoir simulation. So there is an open source for reservoir simulation.
I don't know if there's an open source, but as far as training in reservoir simulation, it's interesting you mentioned that. Advantage India actually has a training right now on reservoir simulation, so you may want to reach out to them. And they're trying to do they're trying to hold some well modeling classes. So I would connect you to Advantage India. They're privately held and they are holding classes in reservoir simulation.
So if any student have any other doubt, or we are concluding this session now.
Thank you so much, ma'am, and thank you, sir.
So students can post their feedback in the chat box and they can leave the session. And thank you very much, ma'am, for sparing us your valuable time and giving the insight on this reservoir simulation. And thank you to our principal, sir, for sparing their time. Thank you. So we can conclude the session here, ma'am.
All right. Talk to you guys later.
Yeah, sure, ma'am. Thank you again.
Bye-bye.